So we're into section 9.3, which deals with logarithmic functions, right? 9.2 was exponential functions, so now we're into logarithmic functions. Now, I had said probably in the last set of videos maybe that we had skipped section 9.1, and really, if we had done section 9.1, it kind of would have explained this whole idea, because section 9.1 is called inverse functions, and that's really what logarithmic functions are to exponential functions. All right. So what I say at the top here is just as multiplication is the opposite, and really that word opposite should really be in quotations. It's not really a true opposite. Squaring is the opposite of square rooting, right? And adding is the opposite of subtracting. Logarithmic functions were created to be the opposite of exponential functions. And really, the mathematical term for this is really the inverse, right? So multiplication is the inverse operation of division. Squaring is the inverse operation of square rooting. Adding is the inverse operation of subtracting. So taking a logarithm is the inverse operation of exponentiating, right? Which is a word we'll get into in the last section, right? So what an inverse really does is it undoes, right? It undoes whatever the initial operation does, right? So like if I multiply by 3, I would undo it by dividing by 3. If I was squaring, I would undo it by taking the square root. If I was, adding 5, I would undo it by subtracting 5. So just like if I'm exponentiating, I can undo it by taking a logarithm. Okay? So this statement that I have down here gives the relationship between exponents and logs, right? So if b to the k equals x, right, where we call b the base, k the power or the exponent, so if that's equal to x, then log base b of x equals k, okay? And that's how you would say that. When you see this phrase here, what you say is log base b of x equals k, right? When you see that, that's what you would say, right? The log base b of x equals k. So the thing you should note here is that these two statements are really saying the same thing. They're just saying it in two different ways, right? The first one would be exponential form, and then the second one would of course be what we're just doing now, logarithmic form. All right. And another thing to notice here is that whatever the base is in the exponential form is still the base in the logarithmic form, right? B is the base here, and b is also the base over here. The only thing that switches really is the k and the x, right? In the exponential form, the k is the exponent of the base, whereas in the logarithmic form, we're taking the log base b of x, and it's equal to k. So really what you can think of it as is the base is staying the same, and then the other two numbers or values, whatever you want to call them, are switching places. So k and x kind of switch places here. All right. And what I usually tell people when I do this in class is think of this like in English, how you have the active voice and the passive voice, right? So there's two ways to say something, right? You can say it in the active voice and the passive voice, but it's the same thing, right? So like if I say I am writing on this page, right? I write on this page would be the active voice. And then I could turn it into the passive voice by saying this page is written on by me, right? So I write on this page is one way of saying it, active voice. This page is written on by me would be the passive voice, but it's really saying the same thing, just two different ways. That's what we're doing here with this exponential and logarithmic form. We're just saying the same thing two different ways. Okay, so just like when we did exponential functions, where the base could be any positive number, logarithms also are going to exist for any positive number base, right? So we can take the log of any positive number, right? The log of any positive number base. Although the most frequently used ones, of course, are base 10, which is going to be called the common log, base e, which is going to be called the natural log, and base 2, right? And if you look really briefly on your calculator, you can see you actually have this button here that says log and this button here that says ln. And the button there that says log is really the base 10 log, and the button that says ln is the base e log, which is known as the natural log. Okay, so those two bases, base 10 and base e, are actually programmed into the calculator. Okay, so really the key concept to remember is that a logarithm is an exponent. Okay, so if they're asking you to evaluate a log, like log base 2 of 64, you got to realize you're finding an exponent. Okay, so what you're really asking yourself when you see this is, you see log base 2 of 64, what you're really asking yourself is 2 to what power is going to give me 64? So what I do is I think of this like a thinking cloud, right? Here's the statement, log base 2 of 64, and what do I think? I think to myself, 2 to what power is going to equal 64? Well, that would actually end up being the 6th power, right? So if they say evaluate log base 2 of 64, it's going to be 6. And again, why is it 6? Because 2 to the 6th equals 64, right? So log base 2 of 64 would be 6. And of course, you can write then that statement in two different ways. The log base 2 of 64 equals 6. That would be the logarithmic form. And why is that so? That's because 2 to the 6th equals 64, right? You're really saying the same thing there, just two different ways. One exponential form and one logarithmic form. Okay, so that's this first little exercise that I do here. I'm converting from exponential form to logarithmic form. So my first exponential form is 10 to the 4th equals 10,000. And the thing to note here is, when I see log, and remember I showed this on the calculator a minute ago, log is really log base 10, right? So if you just see the word log without a base written next to it, it's assumed to be base 10, right? So when I'm going to turn 10 to the 4th equals 10,000 into logarithmic form, what is it? It's just log, right? It's base 10, so I don't need to write any base next to it. And then remember what I said happened? These two numbers just kind of switch places. So it's the log of 10,000 equals 4, right? And then the same thing here. 5 to the negative 2 equals 1/25th. I would write this as log. Remember, the base stays the same, so it's log base 5. And now these two numbers switch. So it's log base 5 of 1/25th equals the exponent, which is negative 2. So log base 5 of 1/25th equals negative 2. Okay? And then 7 to the 0 equals 1. This would be log. Base stays the same, so it's still base 7. And now I switch these numbers. So it's log base 7 of 1 equals 0. Okay? And then just like log base 10, we just write the word log for it. When we have a base e, we use ln. So ln is really log base e, right? And really, if you ever wrote log base e or log base 10 like on a test, I would take it. It's just that it's not the conventional way of writing it, right? So log base e is going to be written as ln. So when I have e to the negative 1 is approximately 0.368, I can write this as ln, right? Because that's log base e. And then again, these two numbers switch. So it's the ln of 0.368, and that's approximately equal to negative 1. Now, is it exactly equal to it? No, but it's very close. And that one I can actually just look at on the calculator. Right? If I went to the calculator and I typed in the ln of 0.368, right? Type in ln of 0.368, and what do I get? Negative 0.999 something, right? So it's approximately -1, right? If I rounded it to even, what, 3 decimal places, it would still be -1. So ln of 0.368 is approximately -1. All right, so that was just changing from one form to another, right? But the other kind of things that you'd be asked in this, in this section is they'd ask you things like, all right, evaluate log base 2 of 16. Evaluate log base 4 of 1/64th. Evaluate log base 8 of 1. Evaluate log of 10, so on and so forth, right? So when you're doing these evaluating problems, it's useful to think in terms of exponents, right? So remember my thinking cloud here. So when I have log base 2 of 16, what I'm asking myself here is, in the cloud, 2 to what power will equal 16, right? Over here I'm asking myself 4 to what power will give me 1/64. Here I'm asking myself 8 to what power will give me 1. And over here, remember this is base 10 because it's log without a base written, so it's 10 to what power will give me 10, right? So those are the questions I'm asking myself here, and now I would just, evaluate all these. So 2 to what power will give me 16? Well, it's 2 times 2 times 2 times 2, which is going to be the 4th power, right? 2 to the 4th equals 16. So log base 2 of 16 equals 4. 4 to what power will give me 1/64th? Well, 4 to the 3rd will give you 64, right? But remember when you had the reciprocal here? When you did the reciprocal, that was a negative exponent. So this is actually going to be -3, right? If it was log base 4 of 64, it would be +3, but it's log base 4 of 1/64th, right? The reciprocal. So when you see a reciprocal like that, you know it's going to be a negative exponent. Okay, so that's -3. And then log base 8 of 1, well, 8 to what power will give you 1, right? Anything to the 0 power will give you 1. So log base 8 of 1 it actually equals 0. And then over here, 10 to what power will give you 10? Well, 10 to the 1st, right? And those two ones at the end there are actually special ones that we're going to actually write as properties of logs in a second. But you see how I said converting to exponential or radical form can be useful? You could get a tricky one. I have to just add another one to the side here. The tricky one would be something like, all right, log base 4 of 2. And this one is tricky, right? Because this one, what you're thinking is 4 to what power will give you 2. See, I could see people saying 2 here because they might reverse it and they might say, all right, well, 2 squared is 4, so it's going to be 2. But no, you're saying 4 to what power will give you 2. And this is where I had said at the top, it can be useful to convert to sometimes radical form because that's what we have here, right? 4 to what power will give you 2? Well, it's really the square root of 4 that's equal to 2. And if you remember when we did radicals, we said radicals were really fractional exponents, and the square root was actually the 1/2 power, right? So log base 4 of 2 was actually a half. That would be a tricky one, right? Whenever you're dealing with a radical like that, it's going to be a tricky one, right? Because it might not be obvious, okay? But really, the thing to keep in mind there is you're always looking for an exponent, okay, when you evaluate logs.